everyone, so today we're going to be talking about slope and slope-intercept form in real-life context. And we're going to look at it different ways, but today we're going to look specifically at slope-intercept form. Now, you know slope-intercept form to be y equals mx plus b. But in most real-life examples, we don't use x and y. We use variables that represent like what we're talking about. So here's a really good example. Mark started the day working with an irrigation pipe. He used the equation L equals 15s plus 120 to determine the total length of the pipe as new sections of pipe S were welded onto the end. So you can notice, number one, that they're giving us some information, and I'm hoping that you see it is kind of in that form, y equals mx plus b. So L is the total length of the pipes, which they told us, and S is the number of new sections of pipe. So I actually graphed this. Now you might notice I only graphed it in quadrant 1. Well, that's because most real life scenarios are going to occur in quadrant 1. So what I want us to pay attention to is that B, that y-intercept. When we're talking about real life examples, this might look like the starting point for this. And that's telling me that the pipe was actually 120 units long when it started. And then the 15 represents the slope. So what's the slope? It's 15. Well, what does it represent in the context of this problem? Well, it actually represents, remember we talked about it as a rate of change. And we always want to try and get that rate of change in terms of 1 unit of whatever the S is in this case. So for every 1 section of pipe, the length increases by 15. And what's the y-intercept? Well, we said the y-intercept in this case was 120. And what does it represent in the context of this problem? It represents the starting length of the pipe. Now let's look at that again. The 15, for every 1 section of pipe added, the length is going to go up by that 15. And that's how we interpret slope-intercept form. Now let's break it down. You're used to slope-intercept form in the form y equals mx plus b, which we will see examples like that. Now m, I want us to think of that. It's a rate of change. Rate of change, so it is the changing value. B, again, in a graph we call it the y-intercept, but in real life we would think of it as the starting amount. Now, this can get a little trickier when we flip it around. This is the same form of the word. We use the commutative property to flip it around, and I put the y-intercept first. Well, in real life, that kind of makes sense. This is my starting place, and then I'm either adding or subtracting something that's changing. So I want you to feel comfortable with each of them. It's important to pay attention to where the x is, because the slope, or the rate of change, is going to be with the x. Why? Well, because x is going to be a number I'm going to plug in to help it change. All right, let's look at some more examples. Here we've got farmer Allison had a well on her property 200 feet deep. When the well went dry, she hired a company to drill the well deeper. She used the equation D equals negative 75t minus 200 to find the depth of the well using the number of days the company drilled, and they called that t. So they told us what the variables represented. D is the depth of the well, and t is the time in days. So what does the 75 represent in the context of the problem? Well, the 75 is the rate of change, right? It's the slope. So what does it represent? For every day, because t is days, for every 1 day, the depth decreases by 75. Why is it decreasing? Well, because it's a negative slope and we're digging deeper. We're going down into the ground. All right, let's look at another example. Christopher had $125 in his savings account to buy a used car. He used the equation A equals 125 plus 50W to determine the amount in his savings after depositing the same amount in his account every week. So W's weeks, A is the amount in his savings account. If I think about that on a graph, here we go. We've got weeks and we have the amount in the savings account. All right. Well, I noticed that this is in y equals b plus mx. So that 125 is my starting amount. That's the amount he started with in his savings account. And 50 is my slope. So what does the slope represent in the context of this problem? Remember, we want it in terms of the rate of change. So for every 1 day, or every 1 week, the amount in the account increases by 50. So a graph of that, it's going up. We're putting money in the account, it's increasing by 50. This one's not taking into account any interest or anything like that. All right, let's look at another one. Jose the plumber charges $65 per hour to fix your plumbing. He uses the equation 100 plus 65H, or C equals 100 plus 65H, to determine the charge of his services after working H hours. So I can see that C is on the y-axis, okay, and that's the charge, and H is the time along the x-axis, okay, in hours. All right, now that it's asking me something different, it's asking me what's the y-intercept. Well, remember the y-intercept is the starting amount. So what does it represent in the context of this problem? Well, if it's the starting amount he charges, it's really like his service charge. The amount he charges to come over. The amount charges to show up. Okay, so it's starting here. It's $100 no matter what. And then it's going up by $65 per hour. That per is one thing I always look for, which indicates it's changing based on the amount of hours, which indicates it's the slope. So we always want to look for the word per hour, per day, per month, per unit. Okay, couple more. Actually, just one more. Laura lights a candle in her kitchen. The height of the candle is represented by the equation y equals negative 1/2 x plus 6, where x is the time in hours the candle's been burning, and y is the height of the candle in inches. What was the height of the candle before Laura lit it? So think about this. We've got the height of the candle is x. Is y, and the time is x. Now I look and my slope is actually negative. So we've got this candle. It starts at some point and it's going down, okay, like this. So what was the height of the candle before she lit it? Well, it would be 6 inches. That's the starting amount. So I want you to think about this very clearly. I want you to think about what the x-intercept would represent in the context of this problem. So if this is the starting point and then it's going down by 1/2 inch each hour, what would this point mean? Well, hopefully you're thinking it's when the candle's burnt out. No more candle. It's the x-intercept, and it means that that's the amount of time for the candle to burn completely. Now, I know that there's a couple other examples on this sheet, okay? Ooh, so completely. I can't spell today. There's a couple more examples on the sheet. I want you to try them and see how you do, and we'll talk about them tomorrow. Have a great day.